All right, so this is our first lecture on microprocessor and the addressing mode. So we'll first talk about the microprocessor and learn about how some very brief information about it, and then we'll talk about the instruction set. So again, microprocessor is the central processing unit of any microcomputer. It's actually also the central processing unit of any digital devices, right? So it's actually it's just a chip, which is a very integrated digital circuit. It's a very big chip, but so integrated. It's, you know, it looks very small, but it's very integrated. So we have many generations of microprocessor, like 4-bit, 8-bit, 16-bit, 32-bit. The ones that you have in front of you, most of these are 64-bit, right? And these bits means that, for an example, if I make it simple, as I said before, that the microprocessor, the only arithmetic operation it does is addition, right? So if it is a 4-bit microprocessor, that means it can only handle an addition of 2 4-bit numbers, which is really very small, right? And if it is a 64-bit machine, it can handle an addition of 64-bit addition at once. But if you have a number which is bigger than that, it can still do it, but it needs multiple steps to do it, okay? So as you guess that if you have less number of bits, that means your processor will need more time to do the same addition, right? Because it needs more steps to do the longer additions. So that's why you know, as you have seen probably before, that we are running after higher bits, right? Because if you see, oh, we have a new microprocessor in the market, which is 128-bit, right? It's probably going to that direction, right? At some point it will be 128 or maybe 256-bit, because they're modifying the architecture. At the same time, they're trying to see whether the microprocessor can handle more longer number of bits in the addition or in comparisons in every single operation it does. I tried to also give an example here. So again, even if I tried to write based on the microcomputer here, I think these days the microprocessor is everywhere. Pretty much every single digital device has some sort of microprocessor. Okay. So but in this class we will mostly concentrate on a family of microprocessor manufactured by Motorola, and the name of the family is M6800. Okay, that's why you will see this number. I'm saying this family number in almost everywhere, meaning our manual, our textbook. You will always see this number because this is the series of microprocessor that's called actually family of microprocessor manufactured by Motorola, and we'll be using one of the microprocessor from that family, okay? And we'll be using the instruction set of that microprocessor, okay? I'll give you the instruction set and we'll talk about the instruction set soon, but before we start, let's look at a little bit about how the microprocessor works. This is a very old, but very basic microprocessor or microcomputer architecture, okay? This is a very old one. I'm saying probably people see this for the first time. I'm saying whenever they learn about the computer, how computer works. But this is still true as of today. I'm saying we have so many modifications, updates, changes, but still this is here. Okay, now in a basic computer or any computing device, what do we have? We have a microprocessor, okay? But we also have memories. I'm talking about the RAMs, right? We have memories, and we also have input-output port, meaning, what do? Let's say we are the outsider, right? Because we are in the outside world. We give input to the machine, right? And we expect some output from the machine. So we need some, communication channel. And input-output is the communication channel which you use to communicate with your microprocessor. But whatever you do here, meaning in your computer, in your cell phone, or in any digital device, let's say you are tapping something or you're typing, you press something in the keyboard. At the end of the day, you are actually giving the instruction to your microprocessor. You probably don't realize in this manner, but that's true. That whatever you are doing here, even if you click a mouse, you are actually giving some sort of instruction to the microprocessor. And the microprocessor is the one who actually follows every single instruction you give, and it actually executes those, right? And for execution, it needs memory, right? So here you can see in one side we have address bus. Address bus means, for an example, if microprocessor has to deal with the memory, as you can guess, the memory is a very, very big location where you have plenty of data, right? Now, let's say you ask microprocessor to do something. But to do that, microprocessor has to pull some data from the memory, right? And the memory is a very big location. But how does it know that what the data is? Think about this. You have a memory, and in a memory, every single bit is either 0 or 1. There is nothing else, because everything is written in binary, right? How does it find something it needs? The only thing, I'm saying, the only way you probably have for microprocessor to find something from the memory is the addressing. Because just like let's say we all live in Memphis, but how people find us? Because we have an address. And my address is completely different than yours because we have a unique address, right? Similarly, in the memory map, memory locations, in the memory, every data has a very specific location, and they have an address number, okay? Starting from 0, 0, 0, 0, okay? Now, for an example, if I say that, okay, I have a computer where my addressing is 16-bit, okay? What does it mean? This means that all the memory data I have, or all the types of memory locations I have to address, I can address using 16-bit number. Okay, now think about this. If I have only, let's say, 8-bit number, how many different numbers I can write in 8-bit? Just think about all unsigned number. We know the unsigned, right? Digital circuit. We all know the unsigned numbers, right? So what is the first number you can write in the unsigned? 0, right? What is the maximum you can write in 8-bit? If it's all 1, right? Think about all ones, 8 ones. What is that? Digital circuit class, 255, right? So that means using, we know this, right? So that means using 8-bit, how many numbers you can write? 0 to 255 is only like 256 numbers you can write, right? That means if I give you only 8-bit, at max you can address 256 locations, nothing more than that. Because you cannot write more than 256 numbers. You know what I'm saying? So, but if you have longer, let's say if I say, okay, now I have, instead of 8, I have 16. How many addresses you can write? Much more than that. How do you know how many you can write? So there is an easy way to guess, right? Let's say using 8-bit, I can write 256, right? It's what? 2 to the power what? You can find it always from 2 to the power something, right? It's actually 2 to the power what? So for an example, let me make it very simple. Using 2-bit, just 2-bit, how many numbers you can write? You can write 0, 0, 0, 1, 1, 0, 1, 1, right? So that means it's pretty much like 2 square. Using 3-bit, you can write 2 to the 3. That means 8 numbers, 0 to 7 in binary. So that means using 8-bit, you can actually write 256 number, which is actually 2 to the power 8, okay? Which is 256 numbers. But the numbers are 0 to 255, right? Now, using 16-bit, you should be able to write 2 to the power 16 numbers, which is actually a very big number. You see what I'm saying? Now, think about the address bus. Now, let's say I have 16-bit address bus. That means in my memory locations, I can at max address 2 to the 16 numbers, which is a lot of numbers. What is 2 to the 64? I'm saying 2 to the 16. So 2 to the power 16 is 65,536. It's a big number, right? 65,536. So that means if I have a memory, I have a 16-bit addressing, then I can actually write starting from 0 to all the way to 65,535. Okay? You probably, I'm not sure have you ever seen this before, because let's say if you have a computer, because I had this when I because I had a, just before this ones, the previous computers were all 32s. Okay? Now, my computer was 32-bit, and I installed 4 gigabyte RAMs. Okay? But for some reason, I realized that my computer cannot address more than, it always shows that my memory is 3.2 or 3.3 gigabyte, not 4 gigabyte. That means even if I install the 4 gigabyte memories, it cannot actually address all of them because it's 32-bit. And the maximum addressing it can do is 2 to the power 32, which is not enough to address all 4 gigabyte. And even if those computers here, I think most of those are 64-bit. So there is a restriction. I'm saying you cannot go beyond something, and then your computer will not be able to address all of those memory locations. Now, think about this. I have 16-bit memory locations, memory addressing. This is something different. I have 16-bit addressing. That means if I write in hex, because in this class, even if everything is binary, we'll be writing all the numbers in hex. Hex is the default language of this class, okay? If I write any number in the board, by default that is hex, unless I tell this is not hex, okay? Now, so let's make it a little bit simple. If I have a 16-bit addressing, so that means in hex, my first address is, what is my first address? 0000. That's like 16-bit in hex, right? I wrote a hex number. What is the last address? What is the last one? FF, right? That's the last number, which is actually 6535 in decimal. If you just convert FF to decimal, we know how to convert from hex to decimal, right? So it will be 65,535. But anyway, we'll talk about this more details. I just try to give you a little bit of idea that what is the addressing and what is the data. How actually microprocessor finds something, and what does exactly means by 16-bit address bus. Okay, so that means if it is 32-bit address bus, we'll be able to address more locations then, right? So that means we will be able to accommodate more bigger memory than what we can accommodate in 16-bit. Okay, but we'll be talking about more about this over the semester. Okay, applications of microprocessor. I tried to limit here, but I'm sure it's not here because there are so many other applications. So mostly it's used as a CPU of microcomputers, personal computers, right? We have many video games, calculators, home appliances have microprocessors. We have these days automobile engines, right? Controlled by the chip microprocessor. We have many industry standard machines in factories where we need microprocessor. So we have many other things. I tried to stop here, but I think there is no end of applications. Okay, here is a little bit of idea that how the microprocessor actually find the address in the memory. Okay, these are some giving you an idea that exactly what happens. Let's say this is your microprocessor. Okay, let's say this is your microprocessor. As you can see, this is your memory. Okay, these are some memory locations. Okay, now let's say we wrote these numbers in decimal. These numbers. Okay, let's say this is the first memory location, which is the location 0. You know what I'm saying? This is what location 1, right? Because it's just like our home address, right? Let's say I live in some 1 this road, right? You live in 2 this road, something like this. So this is the next address, which is 2. This is the next address, which is 3. Next address location, which is 4. So these are actually the addressing. Now in every address, you have 1 byte data. You see what I'm saying? So for an example, in the first address, which is address 0, this is the data you have. Do you see the data here? This is actually your data. And the data is what? 8-bit, meaning 1 byte, right? We all know, right? 8-bit is 1 byte, so that's our first byte. In the next address, which is address number 1, we have our next byte. You see, it's 1 byte again. So in the memory map, memory locations, everything is just zeros and ones. But we can still identify them because we know that this is address 0, we have 1 byte here. Next one is address 1, we have 1 byte there. Address 2, we have another byte here, right? So we pretty much have different bytes. Now, let's say, and as you can see, there is a direct bidirectional connection with the microprocessor and the memory. Bidirectional means what? It can either read and write, meaning the microprocessor can either read from the memory and write to the memory, depending on what exactly it needs. Reading means it can read whatever we have in specific memory location. It can read it, okay? Or if it has to write, it will go and write in that memory location. But before it reads or writes, it actually needs to know which address it's actually dealing with, right? I'm saying it cannot read and write at once every location. It has to read and write in a specific location, meaning either, let's say, memory location 5, or memory location 9, or memory location 20, whatever it is. It has to know where it wants to write and read, okay? And there is one single line here, for an example, which actually determines whether the microprocessor will read or write. Okay? So, for an example, as you see here, this is, just by this one, can you guess which, meaning this line can be either 1 or 0. If it is 0, does it write or read? Can you guess from here? Just by looking at this one? Okay. Now, anytime if you see something like bar, you see R is given, but W is given with W bar, right? That means W is the one which works, which is the writing mode, which works when the line is 0. That's why this is 0 bar means 1. Okay? So that means if this line is 1, microprocessor reads from the memory. What does it mean by reading? Reading means the data is transferred from the memory to microprocessor. That's what I'm saying? Memory to microprocessor. And the writing is what? Backward. Microprocessor to memory, right? It's just like a transfer data, right? But we call it read and write. Because read means from memory to microprocessor, because microprocessor is the one who is reading from memory, right? And writing means microprocessor is the one who is writing to the memory, okay? And these are the address lines, meaning the 16-bit address lines. Now, can you read, because these are all binary here, okay? Can you read what this number is in decimal? It's all 0 followed by 1, 1, right? What is this number in decimal? 3, right? 1, 1, right? So that means it's actually referring to this address, right? This is the 3. And this is your data, what do you have in the 3. And if you see, microprocessor is right now in the reading mode, because we said this is 1, right? And if it is 1, this means reading, right? That means it will be reading from memory to the microprocessor, okay? Now, if you look at the data here, what is the data here? 0, 0, 1, 1, 0, 1, 0, 0, right? Do you see that data was read? Look at the data, it read. 0, 0, 1, 1, 0, 1, 0, 0. That is the data we have in address location 3, right? We are just trying to show you how things work. And you might be wondering why the microprocessor is doing this reading and writing and all of this. Is basically, you probably have given or written some instructions somewhere. Let's say you probably click some mouse. You probably have written some instruction. Because just because you click something, right, what exactly happening is some instruction is being executed, right? Written by a programmer, right? Because it's all different programs running in your computer, right? So whatever you do, some instruction is being executed by the microprocessor. And because of that execution, microprocessor have to probably read something, add something, right? Or, subtract something. Again, don't forget, subtract is done in terms of addition. So even if I tell subtraction, addition, multiplication, is all addition. But just for time being, we'll assume microprocessor is doing all those operations. Okay. So let's move on, because we'll be discussing this again and again, and we'll look at some of this again. Now, very important things here, that to do all the operations that microprocessor do, microprocessor needs some memory locations. I'm saying these are not RAMs. These are some registers. These registers are located in microprocessor. Okay, microprocessor actually does all the operation, meaning like addition and whatever you want in these locations. Okay, so we need to know, and we'll be dealing with these registers for this semester, next semesters. Every time we talk about the microprocessor, we'll be talking about these registers from now on. Now, let's look at some registers here. So the first one is called accumulator A. This is a 1-byte register. Okay. Next one, accumulator B, and then index register, which is a 2-byte register. Because some of the registers are 1 byte, some of the registers are 2 byte, but most of those are 2 byte. Okay. Except the accumulator A, accumulator B, and the last one, which is condition code register. Okay. And this is the stack pointer. This is the program counter. Okay. Now, over the time, we'll know about these registers. Okay. I'm saying at this point, I'm just trying to introduce you with the names. But over the time, we'll know exactly, probably some of the registers are a little bit more specific than generic. Okay. So, but most of the operations we do in accumulator A or accumulator B. Those are 1 byte each. The first. Okay. All right. So I'm not trying to explain it, because at this point we're not ready to understand it. So these are the instructions we'll be writing in our computer. Okay. I'm just trying to show you how it looks like. This is actually a program which adds 2 numbers, 2 plus 3. You might be wondering, why do I need to write like 4 lines? Because it's so simple these days. Because in the calculator you can add like 15 numbers together, right? And press a equal sign, and all the addition sum you get. But remember, at the end of the day, whatever you are doing in your calculator, I'm saying calculator you have in computer, or anything you do in the computer, at the end of the day, microprocessor is the one which actually runs some instruction, right? And it actually does the same thing. Meaning, to add one single to add 2 numbers, it at least need 1 to 2 instruction. But still, it does it so fast. You are thinking the microprocessor is so fast, it can basically add like millions of numbers in a second. But it's actually doing the same instruction probably for million number of times. Because it's doing it so fast, you don't realize this is actually, still it needs like 1 single instruction to add 1 single number. You know what I'm saying? We'll look at and we'll explore all of this here, and then we'll probably have a better understanding of the instruction in this class. Now, again, let's look at an instruction. How does an instruction look like? Most of the instruction that we have for the microprocessor, again, from now on, everything we'll be talking about microprocessor is related to the Motorola microprocessor. But don't assume that if you have to learn a different microprocessor, it will not be too different than what we'll be talking here. Okay, it will be pretty similar, a little bit here and there difference. Okay, so this is an instruction from the Motorola instruction set. Motorola instruction set. We'll give you the instruction set. We have the instruction set already in pause. Now, in most of the instruction, you have 2 different parts. Most of it. Okay. First part is called opcode. Okay. And second part is called operand. Okay. Opcode is the one which actually gives you an idea that what this instruction is about. Is it an addition? Is it a subtraction? Is it a multiplication? What it is. Second part actually tells. The second part, you probably will have a data or an address. You see, the second part has a number, right? Like 02. Remember, it's an hex number, right? You also see some symbols here, right? See, there is a $sign. Anytime you have instruction and you have a $sign, that means the number you have following the $sign is a hex number. That means $sign indicates the following number is written in hex. Remember, you can use different number system here. You can use number in decimal. You can write number in binary. You can write number in hex. Okay. okay? It depends on what is the prefix you're using. If I use like dollar, microprocessor knows whatever the number you'll be writing next is actually a hex number, okay? We'll talk about this more, I'm saying, you'll go more, okay? Now, so what happens is, when you actually write this instruction, let's say you wrote this instruction, okay? Because we are writing the low-level language, right? We'll be writing this instruction directly, okay? Then the instruction is decoded by the microprocessor to something like this. You might be wondering what is this? It's just 8602. Remember, this is hex number. Now, how many bytes you have here? 8602 is hex. Remember, every hex digit means what? 4 digits of binary. So that means 86 itself is 1 byte, right? 8 bit, right? 1 hex digit, 4 bit of binary. So this is 1 byte, this is 1 byte. So it's actually 2 byte of instruction here, right? The instruction itself is 2 byte. You know what I'm saying? First byte is the opcode, right? Second byte is either data or an address. We'll talk about this more later, okay? But at the end, the main thing is this. Even if you're writing everything in hex, to make it simple or to make it easily, compact, in machine, microprocessor is all binary. So whatever you see here, like 86, is actually written in binary there. We know how to convert it to binary, right? 8602. I'm saying, but remember, don't forget, these are written in binary. But we will be writing in hex here to make it simple. Okay. Now, before we start anything in this class, whatever we start in this class, we actually need to understand the addressing mode of the instruction. We actually have an interesting set of instruction, okay? Let me first, before I move there, let me first show you the set of instruction that we have. Okay, the set of instruction is actually here. If you go to pause, the very first thing we have is the set of instruction. If I click it here, I'll give you a hard copy today, okay? If I click it here, here you go. This is the set of instruction. So this is a 6-page list of instructions. That means these are the only instructions that our microprocessor understands. And whatever you want to do with our microprocessor, meaning whatever programming you want to write, you actually have to use these instructions, meaning any of these instructions. And for this whole semester, the next semester, we'll be pretty much living with this page, 6 pages. Okay? Anytime you have any question, you need to do any quizzes, any exam, any test, you have any question for me, you'll need these 6 pages. Okay? Now, we'll not be able to understand everything right now, but I'm just showing you that this is alphabetically sorted. Okay? You see, these are actually the instructions. Okay? So, we'll be exploring this instruction. We'll try to understand this over the whole semester, and we'll be using this. Okay? Now, each of these instructions has multiple modes. Every instruction can work in different modes. Okay? The sole purpose today in the first lecture is to understand, just by looking at the instruction, because we don't understand the instruction yet, right? We don't have any idea about the instruction. We just know there is a set of instructions, right? But just by looking at the instruction, even if we don't understand it, can we identify the mode? There is a very easy way to identify it, and we'll just show it here today in the PowerPoint, and then we'll do some practice, and also we'll do some quiz, okay? And I'll give you this hard copy as well, just right after the lecture. Let's go back. Now, these are my 6 different addressing modes. To understand the instruction is extremely important to understand the addressing mode. That's why we are first trying to understand the addressing mode. Okay? Now let's read the names. The first one, immediate. In the parentheses, I wrote the short names. Okay? And these short names are widely used. Even those short names are there in the addressing, the set of instructions. The first mode is immediate, direct, extended, inherent, relative, indexed. Okay? And today, we'll be only exploring first four. We'll discuss the last two later sometime. Okay? So that means we'll be concentrating mostly on the first four. That means what we are trying is this. We'll be given an instruction. Just by looking at the instruction, can we tell whether this is immediate, or direct, or extended, or infinite? This is the purpose of this lecture. Okay? Let's look at the instruction, and I'll try to give you a very, very small, brief hint that will actually help you to identify the instruction. Okay? Which is actually very easy. Now, immediate, the first. If you have to understand the immediate, all you need to see is whether there is a pound sign. You know this is a pound sign, right? But remember, in the computer language, we call it pound. I try to use pound because we know it by pound, because most of the time, you know, people say, oh, just press pound, right? But this is, in computer language, this is called hash. H-A-S-H. Have you ever heard this before? Hash, right? So, you know, whatever you call it, pound sign or hash. So, if you have an instruction where you have pound sign, it's immediate. Okay? That means pound sign should actually precede the operand part of the instruction. Remember, we have two parts, right? The first part is opcode, second part is operand. Meaning, if you have pound sign, that's it. That's immediate, which is very easy to identify, right? So, but I also tried to give you a list of instructions here. I'm saying different types. Now, remember I said, don't forget, I said we can use three different number systems, right? We can either write the operand in decimal or binary or hex, right? But how does the microprocessor know? This is how microprocessor knows. If I use a $ before the number, that means this is hex. If I use a percentage sign before the number, it's binary. If I use nothing before the number, see, there is no percentage sign, no $sign. That means this is decimal. See, the problem is this. 162 can be decimal, can be hex, right? But since there is no $sign, microprocessor knows this is decimal. Okay? That's what I'm saying? I'm just trying to give you an idea. But to identify the immediate mode, all you need to see is whether there is a pound sign or not. You don't have to see what is the number system, but you know, I'm still trying to give an idea what is the number system, okay, used in this instruction. I think the immediate is the easiest one. The next one, direct. If the instruction is direct, then there will be no pound sign. See, right now I have three instructions in my list here. None of the instruction has a pound sign. That's what I'm saying? So for sure there will be no pound sign. What is next? The next thing is your operand. You have an operand, right? Second part, right? Remember, the second part is the operand. In the second part, the operand part will be 1 byte. See, this is 1 byte, right? Remember, in hex, how do I know it's 1 byte? Hex digit is what? 1 hex digit means 4 bit binary, right? So that means this is 1 byte here. This is in binary, right? How do I know this is 1 byte? Because it's 8-bit, right? I'm saying if it is binary, it has to be 8-bit or less. That means 1 byte, right? How do I know this is 1 byte? This is decimal, right? We know this is decimal for sure because there is no $sign, there is no percentage sign. This is decimal. But how do I know this is 1 byte? Because I have to know, right, whether this is 1 byte or more, right? How do I know this is 1 byte? Any idea? No clue? Exactly. If it is unsigned, it has to be less than 255. Remember, the maximum we can write is what? 255. That means all you have to check is whether the decimal number, if it is decimal, it is 255 or less. If it is more than 255, that's not 1 byte. Because you cannot write it in 1 byte. That's what I'm saying? So what is the criteria for the direct? Pound sign. And second, your operand must be 1 byte or less. Right? It cannot be actually less. I'm saying if it is less, that means the remaining spaces should be filled by zeros. I'm saying technically it's 1 byte. You see what I'm saying? Okay. Next mode, extended. Extended, again, has no pound sign. But the operand is 2 byte. Look at all the operands this time. Look at the hex. For sure, this is 2 byte, right? D1, 2, 3. This is 4 digit of hex. This means 16 digits of binary, right? Because remember, 1 hex digit means 4 digits of binary, right? So this is 16-bit, and as you can see in the binary, this is more than 8-bit, right? I'm saying, if it is more than 8-bit, that's it, because you cannot accommodate it in 1 byte. It's 2 byte, right? How about this one? It's decimal, right? Because there is no dollar sign, no percentage sign, so that means the data is decimal, and it's 53539. I'm saying, which is for sure more than 255, right? So that's decimal. I'm saying that's extended, right? Okay. Any question here? The last one is probably the easiest one, because inherent is the only instruction mode where you have no operand. So that's pretty easy to identify, because remember I said most of the instruction has two different parts, not all. This is the only instruction mode where the instruction does not have the operand. There is no operand, it's just the opcode, okay? Which is very easy to identify. I'm saying, because just by here you see there is no operand, so this is inherent, right? Let's now look at some examples. Try some example and then we'll do the quiz, okay? I'm sure we love the quiz, right? So let's try some example first. Okay, now, this is our first one. What is the addressing mode here? You are given an instruction, right? It's immediate, really easy because it's a pound sign, okay? So that's immediate. Let's try the next one. How about this one? Direct, right? Because no pound sign, and the operand is what? 35, which is what? Decimal, binary, or hex? Decimal, right? I'm saying, I just want to make sure we understand the instruction. So this is what? Direct, right? Let's look at the next one. Very easy. Inherent because there is no operand. How about, so it's inherent. Oops. That's what? Extended, right? Is it extended? Okay, first of all, there is no pound sign, so that's not immediate, right? So that can be either direct or extended. But look at the data. How many digits you have? What is the data? Is it hex, binary, decimal? It's hex, right? This is followed by the dollar sign. The data is hex. Now, it's more than 2 digit, right? Remember, 1 digit means 4 bit. See, as long as it's more than 2 digit, that's it. Because it's more than 2 digit, it's 3 digit, that means what? 12 bit. I'm saying, at the end of the day, it will be actually 16 bit because the remaining places will be filled by zeros, right? So it will be actually 0A 2B in the memory. That's what I'm saying. There will be an initial 0A 2B. Even if you write A2B in the memory, it will be 0A 2B because I'm saying you cannot put like 1.5 byte, right? It has to be 1 byte or 2 byte. So it will be 0A 2B, okay? Even if we don't write zeros. So this is extended. Any question, any confusion here? Probably some of you might get confused there by just looking 3 digits, right? But remember, anything more than 1 byte means 2 byte, right? For sure. I'm saying, it may not be, it will not never be more than 2 byte. How about this one? Extended, right? Okay, what is the data here? Decimal, binary, hex? Decimal, right? Because, so just since this is decimal and it's more than 255, right? It's just one more than 255. That means you cannot accommodate in 1 byte. So it's extended. Oops. So it's extended, right? Okay, how about this one? It should be direct, right? But here's the catch. This is actually extended because there are some exceptions, and I have never told about the exceptions, but let me tell you why this is extended, not direct. This is why it is extended. Let me go back to the set of instruction. Remember, we have a set of instruction, right? And I'll give you the hard copy soon. Let me give you the hard copies. Okay, so here we are for, can you read the instruction here in the left column? Is it too small for you? Can you read this? Okay, now let's go back to, what is the instruction? NEG, right? Remember the instruction was NEG? Let's go to NEG because these are all alphabetically sorted, okay? So I'm going to the NEG here. I'm scrolling down. So N should be a little bit farther, MN. Okay, now, here is your NEG. Do you see NEG here? Do you see NEG? Now, every instruction supports some specific addressing mode, which is listed in the column 4. Look at the mode it supports. Do you see it? Look at the 3 mode it supports. Does it have any direct mode? Now, interesting thing is, some of the instruction does not support the direct mode. There are reasons. I'm not going to explain the reason right now. Probably you are not ready for the reason. But there are reasons that some of the instruction does not support the direct mode. So that means even if logically it should be direct, you should always check with the set of instruction. If it says there is no, so do you see there are no direct mode? It said extended, right? EXT is extended, right? Even if it is logically should be direct, but if you don't see the direct there, that means it's extended. There is only one exception in case of direct, meaning in some cases it looks like that should be direct, but we always double check with the set of instruction. If there is no direct mode for that instruction, that will be extended. Okay? That's the only exception. So I just want to make sure that there is an exception. Okay? So I'll give you this hard copy within a minute. So let's go back. All right. So that was the exception because we don't have the direct mode for this one. Okay? Now, any other question that we have? Okay. Now I'm hoping that we are ready for the quiz 1. Okay? Let's go to the quiz section. And let's start the quiz 1, okay? And meanwhile, I'll give you the hard copy of the set of instruction. And remember, don't forget the instruction set is already there in pause, okay? Use that one. Meanwhile, I'll give the hard copy, both side printed, so that it gets a little bit compact, 6 pages.